Okay, so let's finish off our final portion of this chapter and let's discuss briefly blood vessels. So blood vessels form this closed loop leaving from the heart and transporting oxygen and nutrients to the tissues and then having the exchange of materials taking place at the tissues and then bringing black blood with carbon dioxide and waste products to the heart. So, as we're talking about blood vessels, I want to start by making sure that you know the 5 types of blood vessels that we'll see. So we're going to have our arteries, which are the vessels that leave the heart. So right after the heart, we see arteries. Then we have our arterioles. These are smaller than arteries, but not quite small enough to qualify as capillaries. So kind of a transitional type of vessel between the arteries and capillaries. The third one that we're going to see is going to be our capillaries. These are the smallest blood vessels that we'll see, and this is where really the exchange of materials between the blood and tissues takes place. The fourth type of blood vessel that I wanted to discuss is going to be our venules. These are smaller vessels that carry the blood towards the heart. And finally, we have our veins, which are the largest vessels bringing the blood back to the heart. So now that we've had a look of arteries, arterioles, capillaries, venules, and veins, I want to discuss about another concept. And what I find interesting is that all of these vessels will have a similar general wall structure, despite their unique locations and the roles that they serve in the cardiovascular system. So let's have a look of that a little bit. If we look at the blood vessels, we will see that nearly all of them have these 3 general layers. Their proportions may change based on what type of a vessel we're looking at, but they all have these 3 layers. And we're going to start working our way out from the lumen, so the center of a blood vessel. And the innermost layer that we're going to see is going to be tunica intima. I often think of this as a mnemonic that I think of it as being in an intimate contact with the blood inside the vessel. Then we will have tunica media, which forms the middle layer of the blood vessel structure. And finally, we have tunica externa, and that is the outermost layer of the blood vessel wall. We'll have a look of each of these in a little more detail as follows. So tunica intima was the innermost layer. This is made of these simple squamous endothelial cells. And again, remember, the description tells us what type of cells are we seeing here. We're seeing one layer, so simple, and squamous were these flattened disc-shaped cells. And really, when we look at that cell structure that forms the tunica intima, that tells us about their function. So facilitating easy passage of materials across this layer is going to be an important function here. And most importantly, we also see that they are our friction reducing lining. Finally, I would also add that they do help protecting the underlying structures as well. So that was our tunica intima, the innermost layer. Let's have a look of the middle layer. And this is going to be our tunica media. Tunica media is the thickest of these layers, and it's typically made of smooth muscle. There might be also some elastic tissue present there. And this smooth muscle is important for us because this is really what controls the diameter of the blood vessel. So we can do vasoconstriction and vasodilation thanks to this smooth muscle allowing us to change the vessel diameter. And this layer is controlled by the sympathetic nervous system. The final layer that I wanted to talk about is going to be our tunica externa. Tunica externa forms the outermost layer, and it's made of fibrous connective tissue. And this connective tissue structure of the tunica externa really helps us to understand what its function is, which is to strengthen the vessel wall structure itself, but also anchor the vessel to its place. I often show also this diagram to my students after we've talked about the blood vessels general structure, because I really think it's a good diagram in terms of showing that all types of these vessels have these three layers that we're going to see, although they might vary a little bit in thickness. For example, here we're really seeing nicely how tunica media is much thicker in an artery. Notice that layer, it's a thicker than tunica media in veins, where it's not quite as thick in comparison. But we still, regardless of what type of vessel it is, we see these three layers. So now that we've discussed about the general structure of the blood vessel, let's compare a little bit of different types of vessels with each other, and we're going to keep it in a fairly general level for this course. So there are many similarities, but there's also differences. So let's see what's different. The arteries have heavier and stronger and stretchier tunica media than veins, and this is because the arteries do have to withstand the changes in the pressure within them. Then if we have a look of the veins, they have thinner tunica media than arteries, and this is because they operate under low blood pressure. Another thing that we see with the veins that's characteristic is that they have valves that help with preventing backflow of the blood. So blood only moves towards the heart, not to the other direction, even against gravity. We also see that the lumen of the veins is larger than that of the arteries. And the final concept is the concept of venous return. So skeletal muscles help to milk the blood in veins towards the heart. So whenever we're moving, we're pushing a little bit of that blood towards the heart. That's why being still for a long period of time, for example, during military parade, might have negative consequences for a person because their venous return isn't working correctly. They're not getting enough blood returning back to the heart, and that would then impact, for example, blood distribution to the brain and cause them to pass out, potentially. The final specific type of vessels that I wanted to talk a little bit is going to be our capillaries. And capillaries are often only one cell layer thick, so this is where we would see only tunica intima present. And this is to allow for the exchanges between the blood and the tissue. So that's the kind of business end of these structures. We also see that capillaries form networks called capillary beds. And because we have more capillaries and more capillary vessel volume than we have blood volume, we need to choose which capillary networks, which capillary beds are open at each moment. So here we're seeing on the top of the screen, first on the left-hand side, a capillary network that's open thanks to the precapillary sphincters being open. And then on the right-hand side, a capillary network that's closed. So the precapillary sphincters don't allow the blood to flow to all of these capillary vessels, only to the ones that allow us to bypass that region. So this is how we can choose where do we need the blood to be at and where do we not need it to be based on the body's needs. I also wanted to talk in this recording a little bit about blood pressure. And it is an important concept, and it's also going to be a concept that we're going to be talking about in our lab. So I want to make sure that we're appropriately prepared for that. So the blood pressure is the force. So in other words, I guess the pressure that the blood exerts against the inner walls of the blood vessels. So as there's blood inside the vessel, that blood is going to push against the vessel walls as well. And this is necessary so that there's sufficient force to move the materials across this membrane between capillaries and tissues especially. So this is what facilitates the tissue perfusion. We need to have high enough blood pressure for tissue perfusion to happen, but we don't want it to be so high that we end up accidentally breaking smallest blood vessels and having uncontrolled leak as a result of that. Blood pressure is measured as millimeters of mercury. And there's going to be two values that we see for blood pressure. The upper value is what we know as systolic value. So this is what we measure while the ventricles squeeze to push the blood out of the heart. And now there's a high blood pressure within the arteries as a result. And the lower value is going to be our diastolic blood pressure. So this is measured when the heart relaxes and the ventricles are refilling with the blood. So there's not as much force being exerted against the walls of the blood vessels during the diastolic stage. I do want to mention here, though, that the range that is considered normal for humans is highly variable. So we will see that systolic pressures can range typically between 110 and 140 milligrams of mercury, while diastolic pressure ranges are usually around 70 to 80 millimeters of mercury. So it's important that we compare the blood pressure measurement that we get against that specific patient's normal. What's normal for them? So this is why we really record the blood pressure every time you go and see a physician or a healthcare professional. So we build this kind of a record what's normal for you, and we can compare the blood pressure against it. And since our lab in this course will involve you measuring the blood pressure, I do want to go through the basic theory behind this process. You'll get to practice it in person, in a classroom, but I do want us to have kind of a general idea of what's going on there. So first step of this process is here in this picture, I'm showing you the course of brachial artery of the arm. And as you prepare to measure blood pressure of the patient, you can assume that a blood pressure of 120 over 70 milligrams of mercury would be fairly accurate for a young, healthy person. Many students, when they're measuring the blood pressure manually, they end up finding that it is helpful to first palpate the brachial artery at the bend of arm so they know where to find it before you put the pressure cuff and other steps so that you know exactly where you're looking at, where you're placing the stethoscope to listen with. The second step of this process is really to put the blood pressure cuff on. So we wrap the blood pressure cuff snugly around the arm, just above the elbow, and we inflate it until the cuff pressure exceeds that of the systolic pressure. At this point, the blood flow to the arm is stopped as the pressure cuff is now constricting that brachial artery so tightly that it's completely closed, no blood is getting through. And as a result, we cannot anymore hear with a stethoscope or feel by finger that brachial pulse. So that's the second step. Now, in the third step, the pressure within the pressure cuff is gradually being released while the examiner listens, or so that would be auscultates. So that hence the word that we're seeing. They're listening for the sound of the brachial artery with a stethoscope. And when they start to hear this first tapping sound, this is the first point at which a small amount of blood is actually sparking through this constricted artery. And this is the value that we will record as a systolic blood pressure for that patient. And the final step includes us, as the pressure is being reduced still further and further, listening for the sound. The sound becomes louder and more distinct. And finally, when the artery is no longer at all constricted, so it's completely open as that pressure within the pressure cuff has released, the blood flows fully freely and the sound can no longer be heard. This pressure at which the sound disappears is what we record as a diastolic blood pressure. So you're listening when you first hear the sound, and you're listening where you can no longer hear the sound. Like I said, you'll get a chance to do a lot of practice of that in a class, but I do want to make sure that we've kind of covered it at least a little bit. Now, as a next thing, let's look at various factors that can affect one's blood pressure. And there's quite a few. First thing that I wanted to mention is that arterial blood pressure is directly related to the cardiac output and the peripheral resistance. In addition to that, we see neural factors playing a role as well. This is mainly the sympathetic nervous system, which promotes vasoconstriction, so narrowing of the vessels, which will then consequently increase the blood pressure. I also wanted to mention renal factors, so in other words, our kidneys. Kidneys regulate blood pressure by altering the blood volume within our vasculature. If the blood pressure is too high, kidneys can release water from that volume as urine, and that will help us to bring down that blood pressure. If the blood pressure is too low, then kidneys start to release a hormone known as renin. And this renin then triggers the formation of another hormone known as angiotensin 2. And angiotensin 2 is really a vasoconstrictor, as angiotensin 2 stimulates the release of aldosterone, which then enhances the sodium and water reabsorption. We're kind of getting an additive effect, so we're moving back sodium and water to the vasculature so it doesn't get lost as a urine by kidneys. We're seeing kind of two mechanisms at place of altering the blood pressure in response to that too low of a blood pressure by maintaining fluids within the vasculature. I also wanted to mention temperature. Temperature will have a role. So heat has a vasodilating effect, whereas the cold has a vasoconstricting effect. In addition, I would be amiss if I didn't mention chemicals. So various different substances can cause either increase or decrease in blood pressure. For example, epinephrine in particular increases heart rate and blood pressure. And the final one that I wanted to mention is also our diet. It is believed that a diet low in salt and saturated fats and cholesterol prevents hypertension, so helps us to prevent us from high blood pressure. So really, it is an interplay of many factors that are at play at the same time simultaneously. And we're constantly adjusting these factors by the body. We're constantly adjusting blood pressure by the body, both in short and long-term responses. To wrap up our discussion, I wanted to talk a little bit about the pulse. So pulse is what we can feel at the surface of the arteries as a fluctuation between the systolic and diastolic blood pressure. This is useful as it offers us an indirect way to find out about one's heart rate. And a normal pulse varies between 60 to 100 beats per minute. And on this next slide, I wanted to show you that the pulse can be taken from many different locations throughout the major arteries in our body. Obviously, some of the locations are more commonly used than others. So as we come to the end of this recording and the recordings for this chapter, I think we have covered all that I wanted to cover in this video. In a class, if we have time, we will also look at some of the most important arteries and veins. But since this is a survey course, I think that this is a good place for us to stop with this recording. I appreciate you as always for being part of this class, and I look forward to seeing you at the next video. Until then, bye.